All right, Sunday, mid-March, 2023, Seattle, Washington. Well, let's see here. We might begin with recapping what we discussed somewhat over the past couple weeks. And when I say we, it's in the general inclusive sense, and in a general sense of that we share a lot of knowledge, and it's called the canon. And the canon is what we have of scientific knowledge and matters of shared language and library and all such things what make requisite facts of knowledge in terms of the interchange and the exchange of ideas and thoughts that we all can share and that as matters of definition and after the how you'd say derivations that so follow or the declarations and their definitions in what terms of the structure results after declaration and the definition fills in the body, what concepts we entertain come together in a linear and inclusive set of things that we can consider as sometimes what's called the dialectic, that we read two things together and thus that it becomes that their stories are intertwined and in a sense at the same time that they're composable, that they're also separable, that these sorts of considerations in the logic and of the speaking of them and of the manners of things, that for what we mean, what we intend, for meaning and intent, that we can discuss the intentionality and extensionality of things, which is how we say equals, or in terms of a tautology, that two things pull together or pull apart, in the sense that it's a tautology, and that these notions of expression end up having well-defined, well-posed, well-understood words that we can then say that we say. So here I'm reading from Nonlinear Electromechanical Effects and Applications, and what I'd gather would be useful is to explain some of what goes into reading in terms of an unfamiliar edifice of a work with not necessarily familiar text in its contents, and that there's skimming and there is reading. There is skimming for the rapprochement and the rapport with the terms and the terminology and gathering the entire dictionary of words, and then there is reading for detail and reading for comprehension with regards to any particular fact, or in the linear narrative and linear curriculum, what is the, how you'd say, meaning of such things, results that we can look at it both from an outer view and also in terms of when there's an interview, this notion of, again, the dialectic. So what I had done when I had first picked up this book is I had kind of flipped through it and tried to find particular quotes that spoke to me and thus that I relate them to things. So far in the previous readings, we've gotten up to about page 15 and then a brief summary of chapter 1. But now what I'm going to do is skip ahead to chapter 2 after chapter 1 talks of simple special cases of classical piezoelectricity, classical electrostriction, after the theory jointly linear and the piezoelectric coupling, with and without symmetries, and biased piezoelectricity, where bias is generally as of cutting against the grain, cutting on the bias, that it reflects something that's not orthogonal or straight, that there's a bias, which is neither good nor bad necessarily, except in some senses it's bad, and other senses in descriptive it's good that it's descriptive. That he mentions again Gilles Lassant, D. Royer, B.A. Auld, D.F. Nelson, H.F. Tierston, and their works in elastic waves and solids. So then there's that appendix of chapter 1, and browsing up to what was page 40 or so, I'll look to, after the table of contents, what chapter 2 begins to introduce bulk waves for one-dimensional motions. When we can talk about action in one dimension, it's somewhat simplified because in one dimension there's only forward and back. There's this droite and gauche. There's this left and right. We usually orient things in terms of one dimension, in terms of what's called the x dimension, where the traditional coordinate setting, as we draw on a piece of paper that is two dimensions, in a plane, according to Euclid's geometry, that this one dimension is drawn as according to a line or line segment. That one-dimensional motions basically reflect, of course, displacement with respect to any given time, where everything is universally parameterized by time. That he begins to talk about one-dimensional linear and nonlinear motions, and he says that in the absence of external force, we are left with this rho sub r u umlaut sub j equals partial of t ij with respect to xi, that he's holding these inner coordinate settings of this tensor as held constant the other dimensions, that he's resulted that for the region in the one coordinate, or j, is one dimension, that the tensor of I and j is what results that it is pulled out this way. And that has a Piola-Kirchhoff stress tensor. And then Piola and Kirchhoff, it's a hyphenated name, but usually that reflects in the setting that there are at least 2 or 3 people involved with who originated this formula or this definition, that we give people's names to definitions when they are famous for having discovered or written down these notations. And that Piola is one person and Kirchhoff is another, and that then when we talk about different objects of various forms, besides the descriptive, where we would just use natural language words that mean what they say, that then we have these schools of people, that the school of Piola and the school of Kirchhoff have resulted that when we read on after their works and other works developed on them, that we can refer to them in the sense is that we are talking about the particular formula so described as exact and so named and given a name and convention and being a thing. And this is where there's some terms like Euclidean after Euclid or Platonic after Plato, where they've been around so long that they're no longer even proper names. Euclidean written with a lowercase u, or Abelian fields written with or groups rather, written with the lowercase a for Abel. That is basically a commutative group or something like that, and vis-a-vis Euclid and his Euclidean geometry, which has usually these 4 postulates about points, lines, and planes, and then the parallel postulate that 2 parallel lines at infinity don't meet, or this kind of thing. That then the Platonic is all these notions of the ideals, that otherwise then you'll find that things are named for their proper founders of a sort, like Euler and Gauss and Green and Lagrange and Cauchy and Hamilton. And as we talk about these other names of tensors and other quantities and constructions, that their structures are so named. So he has that a Piola-Kirchhoff stress tensor given by this particular combinatorial form that rotates over all these dimensions, because here we're getting up to there's now 5 and 6 dimensions of this thing, or these coordinate axes, or these indices to coordinate axes, that represents usually a product of something in a given number of dimensions with a product of another in given dimensions, and according to their Cartesian product after René Descartes, where his name is usually written Descartes, but when we talk about him, it's called Cartesian, that this product of the Cartesians includes a sum of the dimensions of the terms that are so produced. And so he introduced that, and he introduces a definition, and this is where the first time you use a word, it has no meaning, except in its placement of where it is and what it does. Without so following any other definition, it says so follows how it is defined in terms of these things. So we have a great body of knowledge and words and definitions and terms that they're so defined by their usage, and maintaining a convention for their usage. And then when there's any other considerations to make, like what we hold as constant, or what we hold as fixed, or when we consider that there's only a particular restriction on a range, or we think about that a range is or isn't fully defined, or when we define that things go off to infinity, or that they're limited to a particular scope, that those become conventions and refinements of what we talk about. Note that the nth order coefficient contributes in the n plus 1th order 1, and more generally, all coefficients of order smaller than n plus 1 contribute in the n plus 1th order 1. So what he's describing there, for example, is out of context, that this phrase reflects to anything that has these coefficients that so relate. Where coefficient was defined in an earlier reading of sort, and the order of things is how many, in terms of when you take the product, that these orders accumulate according to these terms, kind of like powers of numbers and their logarithms, or powers of numbers and their roots. That then we talk about the linear equation. He's introducing one-dimensional linear and nonlinear motion. That the linear equation is rho sub r u umlaut j minus this c I j k l u k comma l equals 0. So he's expressing again one of these continuity conditions that, and it's in terms of the arithmetic, which includes addition and subtraction and multiplication and division, usually of the arithmetic of numbers. And we use these operations with regards to things like concatenation or intersection and union, or their disjoints. Here the arithmetic of numbers is used, that we're taking the difference of two products. So that gets into, again, about how sometimes we're able to define things in terms of their products as that they square and fill in area, or square and reduce to 0. That here then there's all these various other constraints that have been built into it, so that it results that we can talk about the arithmetic of subtraction, which would otherwise not necessarily be sensical in terms of that, well, addition is defined by multiplication, and vice versa, in a sense, that after dividing division, you can end up with the parts and how they recompose, and you call that addition, in terms of recursive division and recursive addition, those being kind of either side of the dialectic of arithmetic. That you then get to that here, he's explaining that these constraints that are so applied make it so that, as he so follows, this is the motion equation for a linear and isotropic elastic body crystal. Then he goes on to describe that a solution of equation 25, which is that a solution is any particular input of parameters that, given their evaluation, makes so that the formula holds true, or that the equation holds true, and rather, where a formula is one side of an equation, and an equation is a formula on either side of the equation. That a solution of equation 2.5 is sought in the form of a plane wave. And here he's underlined this and introduced it, where in this traditional typesetting, they don't necessarily have italics and as for emphasis, and so there's not necessarily font or highlighting or any other means to so relay in this typesetting, that the introduction of a definition of a term is simply underlined. And in that manner, that a plane wave is introduced as definition, propagating in the direction of unit vector m underscore I with velocity v naught, where v naught reads v underscore 0 for v naught, nought. Noting b underscore j, its amplitude, and f being an arbitrary function, or a function is a formula, or otherwise that a function accepts as input of terms as parameters, and that it so follows, whether there are other implicit or explicit parts of it, that other things being held constant, it's a function from function theory. We write u underscore j equals b underscore j of the function of the quantity t minus m underscore x, m underscore I, x underscore I over v naught. So when we have to describe in a linear speaking how to write the forms of quantities, there's that we have what's called parenthetical precedence, and this defines the order of the operation or the evaluation of what is a quantity, where in arithmetic they already have, according to these operators, what's called operator precedence. And operator algebra, arithmetic, and operator theory is a theory, and function theory is a theory, and there's arithmetic is a theory, and their objects are primitive and primary in their theories. That equations and formula is, in a sense, an abstract theory. That here, when we talk about quantity, we use the word quantity to reflect the same thing as of reading out those parentheses, so that when we have implicitly, for example, that the precedence of the evaluation of arithmetic is first multiplication, division, assembling those quantities, then addition and subtraction, that here, when otherwise we're collecting a term to be evaluated out of that order and given a different order, for example, when subtraction is of these two terms is to be evaluated before it's so resulted, that's a way to talk about then that for a given function its parameter is a quantity, or that when we have two quantities that are otherwise out of their default precedence in their priority order, how they are so. Then later when we read this next function, or equation rather, carrying this into equation 2.5, we obtain that the quantity C sub ijkl m sub l m sub I minus rho sub r v squared sub 0, or v squared v naught squared, and sometimes you read the superscript first, sometimes you read the subscript first, and when just reading off as these geometrically or diagrammatically arranged characters in a linear speaking. Kronecker kj, so that quantity times b sub j equals 0. And this is an eigenvalue problem for the acoustic Christoffel tensor. Gamma underscore jk of m tilde, and here you use the triple equals bar, c ijkl m l m I equals gamma kj m equals gamma jk minus m, reflecting that according to these properties of this tensor, that is when we talk about eigenvalue and then there's solutions for an eigenvalue problem, it's really is what results what's called the theory of determinantal analysis in the theory of matrices and multiplication. That we're using matrices for these tensors, which are a rectangular array of numbers, and that these tensors also follow these transformation and product rules, that the notation of this what's an eigenvalue problem is that after determinantal analysis, where a determinant is a particular small product or inner product of a matrix that is kind of a quantity that's an indicator, so derived that from a rectangular array of numbers you compute what's called the determinant by basically taking the product of the diagonal, or that otherwise what results is that the eigenvalue problem then results that in these systems of equations of matrices, there's so it follows a way to read off what are these eigenvalues for these eigenfunctions, that in the theory of determinantal analysis, which is a subfield of matrix theory, which is a subfield of generalized matrix theory, and their arithmetics is so defined, and that their operations are closed, that the product of an operation is the same type of thing, or that they are not closed, that the product of an operation like these inner or outer products is a different type of thing, according to Descartes, or the diagonal, in a sense. That he's described these three axes of symmetry about an acoustic Christoffel tensor. When we think of acoustic, it usually means in terms of an auditory setting, and what is a value that is a descriptive term, that the acoustic is as of these waves in their propagation, that there is a particular setting where that the speed of sound is sufficiently less than the speed of light, that an acoustic wave propagates at a very high speed with regards to it being in one medium, or given that sound travels variously in various media, like liquids or solids or gases, but not in space, where there's no carrier in the medium for such what result quantities. And Christoffel is a name, and it describes a whole study of the theory of the symmetries of crystals, which are lattices, in terms of that, if you think of the numbers as an integer lattice, that the lattice work is what so describes for the given points and edges of these crystals, that their symmetries in terms of their centers and the rhombic and such arise. That then he says, let this introduced quantity be the three eigenvalues of gamma. So lambda sub alpha equals rho sub r of v naught alpha squared. So for v naught, as described above, that there's v naught alpha, and that this lambda alpha is that there's three eigenvalues of gamma jk. Now, in terms of the letters that are assigned to variables, in terms of most mathematics, what you'll find is that they come from a restricted alphabet, which is one of either Latin or Greek, and mostly from Latin or Greek. So knowing the Greek alphabet is a minimal extension that allows many of these lettered quantities to be written off when it's necessary to disambiguate between what would be a Latin index, according to, for example, its case or its order or its placement, and what would be another given variable that's often related in terms of that after the Phoenician alphabets, that all these other alphabets basically have an existing character for each of these sounds, that when we talk about alpha, beta, the gamma, delta, epsilon, zeta, eta, theta, chi, rho, psi, omegans, that I've forgotten, that these alphabets end up being a minimal amount of work needed to have a big enough space of letters to fill out disambiguated variables. The fact that CIJKL carries in Voigt's notation to C alpha beta is symmetric, positive, definite, guarantees that the three eigenvalues are positive and in general distinct. So what he's indicating that for a solution of various forms, for example, of x squared having plus and minus I, that these eigenfunctions and their eigenvalues have that in terms of the determinantal setting according to these conditions of symmetries or what operator carries in their algebras these products and as to whether they recycle or are modular or accumulate or reduce, that then there's a notation that Voigt has written where Voigt and Christoffel are very well known in this field, and it's so given to them that what they have established and how they write things is how we write things and how it's established. That then when it refers to the terms that is symmetric, positive, definite, that these words each apart mean something about the state of the things and its description, that is descriptive, and then these words together furthermore enforce more ideal things about the symmetric, positive, definite, that reflects that any given matrix can be in these tensorial forms according to these equations with these product rules, can either be said to be or not to be according to an indicator so generated as from, for example, a determinantal quantity, either meeting the truth value of this predicate or not. Then it begins to discuss polarization, and polarization is a very particular and interesting thing when we talk about the polarization of a circle, that, for example, we think of the North and South Pole, and that when we think of our theory of magnets and electromagnetism, that there's the North and South Pole, and that basically very well reflects what we know of the globe and what we know of the nature of the compass and what we know of the nature of the constancy of that, and that in terms of making an analogy or having a model of what we talk about that there's this and that. Then we also talk about poles in the usual sense of when we write or diagram a dimension. For example, the pole for the x dimension might be the y dimension, or that otherwise it's kind of like the pole of the tent, or what holds a thing up. Then the polarization is a notion that for something that it could swing in any direction, like a pendulum or something along the lines of flagellum of a bacteria or any of this sort of thing, that is free to move around in dimensions, that the polarization is one, it gravitates in a sense as a model of that thing, not necessarily as of the mechanism, that this polarization reflects a particular linearization, even again, of what is called this object in its state. And that to follow, what's key about that is that polarization in wave theory is very involved in light and its theory, that is not necessarily coherent, meaning that it's polarized, and vis-a-vis filters that polarize, given in terms of the orthogonal and the linear and the nonlinear, about how a decoherent light, or otherwise what is the diffuse, ends up being really a key concept, and especially in terms of electricity and electromagnetism, because we start talking about stuff like the three-phase motor, which is what, according to voltage and differential, and what's called the electromotive force, which is that which carries the electrons in an open circuit, eternally carrying around until they dissipate and attenuate their heat to zero. The electromotive force, that the polarity in terms of the electrical current is beyond that electricity is invisible, so that we must explain it by experiment and not via the senses of our eyes. That also polarity is another key feature that's very high level and relates to the nonlinear. That the polar is linear, and that polarization reflects our casting a perspective to a linear setting, and that light is polarizable reflects a change of it, and that light is unpolar reflects that it's nonlinear. And here I'm casting about a bit for a word that means nonpolar. But what it basically means is nonlinear. And that you can consider something that's an extension of the linear basically to be polar. Because of the general degree of anisotropy, these vibrations do not in general correspond to purely transverse or purely longitudinal, which are descriptions of how something is polar, with respect to M vibrations. The values, these eigenvalues, lambda alpha, are obtained by solving that the determinant of gamma jkm minus lambda Kronecker jk, that quantity, taking its determinant, equals 0. So what we have is that whatever so fulfills for gamma as defined above and alpha as defined above, in terms of those for this function, which provides a cubic in lambda for a fixed m. You can see that he's so describing that according to these terms, when we hold these various conditions constant, that they so establish that according to these relations of these functions, that by computing what are accessible values by the fact that these relations in array have been stored in these matrix quantities according to the operators of matrices and their arithmetic, that it so results that then this indicator or determinant can be so computed that the theory of determinal quantities, which then gets into what are called cumulants and what are called orthogonants, though that it is somewhat of an abandoned subfield of analysis, and most of what's left of it since the 30s and 40s of 1900s is the determinantal part of what follows regular matrices and how they're used mostly for the solutions of differential functions according to these eigenvalue problems. That this provides a cubic, which is describing that a function, according to its arithmetic, according to parameter, is third order or cubed, that its rank is 3 for a fixed m. The general solution, which is a solution before it's provided input values of parameters which didn't require reasonable solutions, of equation 2.5 is a linear combination of the three elementary eigenmodes u to the alpha, i.e. u sub j equals the sum for alpha from 1 to 3 of big A sub alpha u sub j to the alpha, where A sub alpha is an arbitrary amplitude. This is where an amplitude is the height of a wave. The eigenmodes and the elementary eigenmodes reflect that a linear combination of them provides a solution where it's that when you think about waves and their signals and their construction or reconstruction and what's called constructive interference and destructive interference of waves, when you add them together, that it so results that he's so defined that we have a term in the third order of arithmetic and that then has a system of solutions then that according to various initial and boundary values may be solved. So then this has been quite a discussion so far of the first couple pages of chapter 2, bulk waves for one-dimensional motions, and we've about described what he's written of linear motion. Thus, to finish that out a bit, let us introduce the director cosines of the three eigenmodes by L sub j to the alpha equals quantity b sub j to the alpha over quantity square root of b sub I alpha b sub I alpha. Now, I'm not sure in that notation why he would take the root of those two terms that are same, and so I'd wonder whether that's a typographical error, that otherwise you'd normally don't write things that are explicit when they can be left implicit. And the root of taking two quantities, their product is always the same as the product in its principal square root. And so that L sub j alpha equals b sub j alpha over root b sub I alpha b sub I alpha, comma alpha fixed. That again, and he's written here that by taking alpha fixed as a constraint and a condition, it so holds that other things that would vary do not. The L sub j alpha equal 1, 2, 3's form a new triad of orthonormal vectors, hence a Cartesian basis. Remember when we mentioned Descartes and the Cartesian that the product of these 1, 2, 3 bases reflects a three-dimensional orthonormal vector space on which the motion can be described. Each mode is then characterized by a scalar displacement, u to the alpha, which can be expressed in terms of the curvilinear abscissa. And here's the symbol, it's called the abscissa, of m dot big X equals m sub j x sub j, so that you're seeing that this inner scalar dot product can be written as this product of the terms each in their dimension. The u to alpha equals big A sub alpha u sub j alpha L sub j alpha. Substituting from this in equation 2.5, we obtain the rows R, the region, the sum over the alpha, and he's left out, equals 1, 2, 3. It's just to indicate over each. That u umlaut, which was introduced as the Piola-Kirchhoff stress tensor's contribution to the one-dimensional linear motion, L sub j alpha, which was just introduced as the director cosines from trigonometry, cosine, sine, and tangent, those forming various constructions as about the circle in the triangle, minus quantity c ijkl sum, capital Greek letter sigma for sum over what is written over alpha m sub l m sub I l sub k to the alpha u to the alpha. The abscissa equals 0. This vectorial equation, three components, can be projected on the basis L super beta in brackets, indicating it's constructed to form the outside quantity, on account of the fact that L sub j alpha L sub j beta equals Kronecker, or delta rather, super alpha beta, that L sub k alpha L sub j alpha equals Kronecker kj. We obtain thus that rho sub r u umlaut to the alpha equals lambda sub alpha u to the omicron, or no, it must be alpha, comma abscissa, and that lambda alpha equals the c ijkl after the Christoffel coordinates in the tensors, where c is for Christoffel, m underscore l, m underscore I, l underscore k, alpha, L underscore J alpha. A equals L underscore J alpha, gamma, underscore jk of m L underscore k alpha. So he's written what is in terms of the bulk waves for one-dimensional motions, that usually a one-dimensional motion in a one-dimensional spring is that we talk about the periodic displacement of a perfect spring, which basically is as to a pendulum, and it swings back and forth. It oscillates between 0 and 1 according to its period, and that so by doing that, the perfect spring has in terms of the graphs of sine and cosine over what's called this period of 2 pi radians, which is as regards to drawing it about a circle, that these type things usually define what we call regular periodic motion. And that this linear terms here is then that he's kind of pulled this out in term what's this higher level notion of these terms as with regards to a linear anisotropic elastic body. That it's deformable, it's elastic, and it's anisotropic, meaning a gradient exists. If it's isotropic, there's no gradient. And that in terms of then the gradient through any of these different surfaces, it being 0, if you recall that's the continuity condition, has those balance together and add up in this regions of analytical character that they're to be summed according to operator theory, according to function theory, according to matrix theory, according to arithmetic. And then he'll go on to describe the nonlinear equation, and I'll take some time for that next time. So we've gotten to a few more pages into this, and if there's something to say about trigonometry, a tri for 3, gon is for the polygon, or that with sides, and etry is as a measure, or a trigonometry is a very particular application of a lot of things that have to do with what are called the identities of trigonometric quantities with regards to the circle, whose radius is measured in radians, that it has 2 pi radians is its units of this rotation about the circle, that by tracing the drawing of a triangle as by tracing the corner of the triangle, given that its other vertex is at the origin of the circle, that there's Pythagoras' theorem, which tells us that a squared plus b squared equals c squared, or rather that the root of a squared plus b squared quantity equals c squared. So according to this, we're able to compute vis-a-vis, and excuse me if I'm rusty, the opposite over adjacent, which is either the tangent or the cotangent. But there's the opposite over the hypotenuse, or the adjacent over the hypotenuse, or the adjacent over the hypotenuse is the cosine, and the opposite over the hypotenuse is the sine. Where for a given right triangle, right meaning that at a right angle, one of its angles is that the hypotenuse is the side opposite the right angle, that this theorem holds true, and that according to it, we're able to determine many of what are called identities, and the trigonometric identities in the study of trigonometry and the facility with various well-known quantities like root 2 over 2 and square root of 3 over 2 have and make for various triangles, for example, that are isosceles triangles, isosceles right triangles, where given that one root is 90 degrees and the other ones are 45 degrees, and all triangles angles add up to 180 degrees, or respectively that there's pi half radians and half radian that add up to 1 radian, where 1 radian is also the same thing as 1 pi radian, same thing as 180 degrees. That the trigonometry is a pretty great thing, and it's defined in terms of Pythagoras' theorem, and it's just, then it builds all these identities that when we use for all manners of transforms in higher level analysis, things like Fourier transform, Mellin and Z transforms, and Laplace transforms, and all these kinds of things that are the use of taking out orthogonal functions, because sine and cosine are orthogonal functions, and their product thus has these product transformation rules that in this world of transform theory, that those things can be said to be so for any such pair of complementary functions that in their family makes a pair of orthogonal functions. That trigonometry is, after geometry was the school forever, that then when analysis became the school, that the tools of geometry are fundamental, ubiquitous, and necessary for many and all such manners of these kinds of higher applications. So what I wanted to get to was the point about this, that when we think of trigonometry, we think of the terms of sine and cosine as being drawn by computing the sine and cosine as it evolves around the circle over a given extension of the period with its of 2 pi over its cycles of those, or according to the clock of it, that thus we're able to draw the sine curve or cosine curve, which is a perfectly smooth curve that represents, for uniform periodic motion, an almost ubiquitous solution for such things as springs and what are the usual models of waves for wave motion, which is the motion of the crest and trough of the waves over time. But after trigonometry is that there's a way to consider, starting with an equilateral triangle, then an equilateral triangle has all its sides the same length, and correspondingly all its angles are the same size. That if you unhinge the triangle and then consider each of the other angles a hinge, where a hinge is like a door hinge, and it ranges in terms of ranging from closed at 0 radians and 0 degrees to open at pi radians and 180 degrees, that as you trace following, open those hinges at the same rate so that it goes from being a triangle that you've unhinged the left-hand side where its base is flat, and that the upper and right side hinges open at the same rate, and you trace according to that vertex of the line that so follows, and you flatten that out until the hinges are open, and then you pick that up and fold the triangle back up and then unfold it again and rotate it around this way. Vis-a-vis this trilateralometry, it's also possible to draw the sine and cosine curve. It's another way to, via geometry, make these same orthogonal functions. And so this is a thing that doesn't really occur to many people, and it's a very surprising fact when it's found, and it's kind of one of those aha things that is so contrived that just because among polygons a triangle's angles add up to pi radians, and among any polygon with a higher number of sides that's convex, for simplicity, the angle adds up to 2 pi radians, that then when we think of these terms instead of trigonometry, we can talk about even something like a quadrilateralometry. In trigonometry and trilateralometry, you could have something like a quadrilateralometry. Whereas when you have a fixed regular that its angles are equal and the sides are equal polygon, and that you make it in terms of a hinged apparatus or as a pantograph, or otherwise that it's a tautochrone, or otherwise that over time it has as regular change and evolve at the same rate, that you can draw all sorts manners of these interesting graphs of functions. Then about families of functions that are as the orthogonal in the higher order, what results the possibility to make higher order transform theory, because otherwise we're only ever separating these two complementary spaces. So this is just a note to illustrate that there are lots of subfields of mathematics, kind of like was mentioned, the determinantal and the cumulants and orthogonants and these higher level metrics, or matrices and generalized matrices, or matrices and matroids vis-a-vis tensors, that all these sorts of things end up adding up, that we mostly have to deal, that we all have to share a linear curriculum, then as with regards to how we can apply these things later, that mathematics is ubiquitous and perfect, and there's all kinds of things about it. So now this has really gone on too long, and I'll stop here in a minute. Let's see here. We must quote at least one of the book. Here's Hans Stephanes, and edited by Malcolm McCallum, Differential Equations, Their Solutions Using Symmetries. The coefficients of the different powers of xa must vanish separately. Any invariant of group of symmetries is a similarity variable of any of its generators. Talks about conformal transformations. He goes on to describe when separating the wave equation in Minkowski space in Cartesian coordinates, one obtains a particular solution, plane wave. Similarly, as we just encountered Maugin's definition of a linear solutions of a plane wave. So it's quite a deep book, and there's much going on with it. Similarly, this differential topology and quantum field theory, dynamic light scattering. So then, have a great day, and I hope this finds you well, and you and yours. And next time you think about trigonometry and all the identities, and what sort of results is how we're able to use that to compute things, especially when we have the table of the values already computed, that we can use those to crunch out indicators, the days for calculators, the necessity of having intermediate constructs that provide the computed indicators of what make it possible for us to have a traction or make things tractable in mathematics. That you have a great day, and so long.